And today is going to be a pretty another fairly challenging day with a lot of material. And I think we're going to get through these first four lessons, and then things I hope will get a little less intense. But you asked for climate science, you're going to get climate science. So we have a bunch to do today, and we're going to start with statistics. Feel free to turn your camera on. I see a bunch of non-cameras. And so this will how you look in the video to the rest of the world. Of course, it's just for our group. And the question is, how much statistics has anybody studied? How many people have taken a statistics class in the last 10 years, not 40 years ago, or read a statistics book in the last 10 years? Anybody? Statistics? All right. So this is why some of what I tell you is going to seem illogical or wrong. And the question we're going to look at right now before we dive into climate is how do you determine cause and effect when we have cognitive test scores of men and women that show that men always come out on top? And I want to explain that. When you have a cognitive score or a cognitive endeavor that has a kind of a highest level, like mathematics, physics, chemistry, hard sciences, you find that the people who are at the very top of those fields are mathematicians, or the physicists or the chemists. They're almost always men. And there are some very, very highly qualified women. But when you start to test these things and you look at the test scores, the first thing you have to do is rule out things that will cause systemic errors. And so one of the things is you have to make sure to test people who have the same education, because in the 1950s, if you gave an IQ test or something to the population, you'd find that men are smarter. But now if you gave it, you'd probably find that women are smarter, because women have more access to education now. And there's more women, slightly more women in education. The other thing you have to watch out for is training, because you can train to take tests, and many people do. And those people with training do better on the test because they know how the system works. So if you flatten those out, if you account for those, and you just look at test scores for difficult cognitive endeavor or areas, and IQ is a ridiculous test that no one should ever take. It's just another one of these one number things that got made up to score people. It doesn't help at all. But if you look at certain types of tests, what you see, if there's a normal distribution, everybody's familiar with a normal distribution, like a bell curve, right? Then what you see is that men are always out at the very front. And an example of this is there is a guy in England who can give you 70,000 digits of pi. Takes him about 2 days to recite. And if you write every one down after he tells you to, and then you put it into a computer, it checks out. Every one of those 70,000 digits is correct. And you can't compute it. The only way to do it is to memorize it. And he has. And this is, I forget his name. He's a savant. A few movies have been made about him. There are these savants, these people that are just way out there on the upper end of cognitive ability in certain areas. Memory is one, navigation, math, theory. There are others. And you find that these people are always men. And in fact, they can't be women. And this is what I want to talk about, because what I'm going to say is Daniel Tammet. Is that the name? Awesome. If you have seen the movies about him, he's amazing. But these people also can't make breakfast beyond putting, milk on cereal. They can't pay their own taxes. They're specialists, right? In some area. And these are the savants. And what we find in testing is that men have in their distribution of results, that men are in a flatter, lower distribution that is wider, and women are in a narrower range that does not have the long tails or the long wings. And men have more variance in their abilities, which means, first of all, I'm right. You can look this up. Men tend to dominate the very highest levels of performance. For example, the Fields Medal and the really esoteric theory areas are dominated by men. And we're going to get to it. But they also dominate the bottom area where people are absolute idiots. They're more, all the total idiots are men. And that's because of this distribution shape. And women tend to cluster more around the mean and have less variance. And I want to explain why, because this is very good work by statisticians to figure out cause and effect here. I never could have, I mean, maybe if I put 10 years into it, but this is really interesting and I want to break it down for you. It turns out that this has to do with the X chromosome. We all know that men have an X and a Y and women have two X, right? And a lot of our cognitive abilities come from this X chromosome. So men get their X chromosome strictly from mom because they got their Y chromosome strictly from dad. Okay. And women get two X chromosomes, from one from dad and one from mom. Okay. So they get their father's X chromosome and they get one of their mother has two X chromosomes and some combination of those two gets put into the other one. All right. So women have two. So if you think about it for a minute, because we know that there are recessive traits. Anybody studied a little bit of genetics? If you studied genetic diseases like Tay-Sachs or sickle cell, you know that it's when two parents have a recessive gene. This is true with inbreeding. When two parents bring a recessive gene, when a child inherits two recessive genes, that child can get the disease or the condition that codes for. Whereas if the child has one recessive gene and one dominant gene, the dominant gene wins. And so the child is protected from that condition. Make sense? So, and this is all for example, if one parent has brown eyes and one parent has blue eyes, what's the deal? 3/4, 75% of their children will have brown eyes and 25% will have blue eyes, right? This is dominant and recessive. Okay. And so what we have with the X chromosome is that when there's a defect in the X chromosome that could make you a savant, that's recessive. The women have another chromosome that can back you up, and then so it doesn't happen. This is called genetic buffering. So women have two chances to get a more normal, two chances to get a more normal gene in any particular allele or gene, so that women don't end up with the recessive traits as often, and men have one X chromosome and they've got to go with whatever's on there. They don't have a choice. Their body can't, there's no way to, compensate genetically, but women can. And that's what gives this shape of less extremism, less variance for women. And men have to go with whatever's on that chromosome. And so they have more extremism. So you get more dummies and more brilliant people from male population than you do from women. All right. So I don't do this to piss people off or to be sexist. I'm trying to help you understand that statisticians can work these things out and often are much better at figuring out cause and effect than psychologists or someone else who has some other wacky explanation for why men, because a lot of people, there's papers about it, that women have these potentials every bit as much as men. But that's not true. The person who knows the most numbers of digits of pi is always going to be a male because he has a chance to have that recessive trait, whereas women don't. So that's hard, and it can get you in trouble. It got the president of Harvard in trouble, Larry Summers, about 15 years ago, and he was fired for saying it because people don't understand statistics. They don't have statistical training. As well, if you look on the community, I have a link to a video I made on Bayesian reasoning. Has anybody seen that? You can find it. I made a video more than 10 years ago on Bayesian reasoning, and that video has a quiz in it that I want you to take. It's about a 10-minute project. So look for the video that I made on Bayesian reasoning and take the quiz. So now we are going to jump into the greenhouse effect. And it is going to be hard and I'm going to break it down into 4 sections. And at the end of each section, I'll just check, come up for air and make sure people are okay. It's not going to be easy. I'll do it the best I can, and so not go too deep. But at the end of that, you'll have a very good idea of how the greenhouse effect works, and you'll be able to watch this video again later. And at the end of that, we'll have our conversation to discuss how we understand it. This is as magnified as I can make it, so you're going to see some small things, unfortunately. I want to start by talking about the sun. I assume everybody's read the little homework that I gave you on the photon journey. And if you haven't, it's there. Download it and read it. But we're going to be using that today. The sun emits high energy photons. And at the core, that's where the photons are made. And the photons are made from an atomic reaction that turns 2 hydrogen atoms into 1 helium atom plus a bunch of gamma rays and other photons, a bunch of electromagnetic energy, because that's E equals mc squared. The mass lost is given off in energy, and it's tremendous. Okay, that's the mc squared part. And a photon starts at the very densest core of the sun, where the density is 150 grams per cubic centimeter. 150 grams. Now, by contrast, the Earth's core is 13 grams per cubic centimeter, and it's mostly iron. And for calibration, how many grams is 1 cubic centimeter of water?
1 gram.
1 gram. That's the definition of a gram, right? We all remember that from high school. That's how we define a gram. So the sun is 150 times denser than water at the core. All right, now once a photon is generated at the core, how long do you think it takes until that photon makes it out to the surface of the sun and then can escape and radiate to space? How fast is the speed of light?
93, no. I've forgotten. Sorry.
186,000 miles per second, or 300,000 kilometers per second. That's the speed of it's going the speed of light from the beginning. How long does it take to get out? 150,000 years to get out. So a photon that comes to Earth has been around for 150,000 years plus 8 minutes. That's on average. Some photons speed out at after 100,000 years, and some take the long way and come out after 200,000 years to get out of the sun. It's very dense, all right? It's going the speed of light. Now, once those high energy photons land on Earth, they hit atoms. They make new atoms speed up. Atoms jiggling is the definition of heat. So they increase their temperature. Then those atoms radiate new long wave photons away in all directions, according to whatever temperature those items are. We'll get to it in a second. Long wave photons are called infrared radiation. I used to think that infrared radiation is the same as heat, but that's not true. These are photons. They are going the speed of light. If you've used a thermal imaging glass like this camera, you can see warm things far away. You can't feel the heat, but you can see the heat because it's radiating out as photons at the speed of light. These are long wave photons. The warmth comes when those photons hit atoms or molecules like air molecules, and then those molecules transfer their energy to your skin. So every single temperature of anything has its own corresponding long wave photons that radiate out at that wavelength of that temperature. This is the Stefan Boltzmann equation. Remember that temperature is speed, so there are always long wave photons hitting atoms, raising their temperature, re-radiating out again. Photons are not heat rays. There are no heat rays. There's just kind of a convection or cascading mechanical transfer of energy to your hands. So here's how it breaks down. This is the visible light spectrum. Look at the left side. The short wave radiation is shown in red because it has more energy. That's the only reason it's red. And it's coming in, not going out. So everything on the left side, I think you can see my pointer, yes? Anything under 3 microns is coming in as high energy photons. Everything above 3 microns is leaving and going out as long wave energy, okay? Shorter wavelength on the left, higher energy on the left, longer wavelength, lower energy on the right. And so here is the visible light spectrum in here. This is the light we can see. This is violet on the left and red, orange on the right. Okay, and then this is a bunch of red light that we can't see. So in the full spectrum of electromagnetic radiation, we want to discuss the right side because this is where the greenhouse effect is. And we'll come back to this. I'm just introducing it. Okay, that's part one. Now, part two is the emission height. This is for the Earth. This is the lapse rate, the bottom part of the lapse rate that we know. The higher, the colder, as we say in grade school. When you're standing on the Earth, as you hike up the mountain, you go down in temperature until you get to the tropopause. So this is a smooth temperature gradient that connects the surface to space via a gradient of temperatures in the atmosphere. The coldest place in the atmosphere is the tropopause, which is where the weather ends and where the cloud tops are. Above that, there's no weather, and that's just where the planes fly. And this is about minus 40 to minus 60 degrees Celsius. It's very cold. That's why you don't open the window when you're on the airplane. And there's really no weather above that. This is the stratosphere then. But it's the coldest here, and then it heats up. And if some people remember my conversation with Mike, it heats up because of ozone up here. When there's moisture, you lose 9.8 degrees Celsius per kilometer. But this lapse rate is different all around the world. It depends on the altitude you're starting from. It depends if there's temperature inversions, pressure systems. There's no standard lapse rate. This is just kind of one that's calculated for certain conditions. All right, now I'm going to convert that slope to this gradient. It's the same thing, right? This is just the same thing. It's just visually different. And it's about minus 50 degrees up here. And then it's about, 15 degrees down here, whatever it is. And we have a single photon that is 150,000 years plus 8 minutes old, and it hits Earth. Now, as it comes in, it could bounce off a cloud and be reflected back to space. That's the albedo. It could be absorbed by the atmosphere, by the cloud, by probably some water vapor, and that would warm it up. But if neither of those things happens, it keeps going straight and it hits Earth. When that photon hits Earth, it's annihilated. Its life is over, and it heats whatever it struck. And that thing it struck radiates long-wave photons out in all directions according to its temperature. And remember, it's about 20 to 1, roughly. One photon in has enough energy to generate about 20 long-wave photons, okay? Roughly. All right, so let's follow one of these long-wave photons as it radiates away. And I'm just going to choose this angle it's just random. All right. What can happen? Well, first, if that outgoing photon happens to be in the right wavelength of 10 to 14 microns, because of the temperature of what it left, then it will leave to space unimpeded. This is called the atmospheric window. It will hit nothing and it will just go off. It will go straight forever. And about 17% of all the photons of all the spectrum are in the 10 to 14 micron range, and they leave in this way. And they don't add anything to the temperature of the Earth. They're just gone. Second, the photon can't, this is where I screwed up yesterday for Nicholas, can't hit an air molecule like nitrogen or oxygen and transfer its energy to that molecule. That's impossible. These atmospheric molecules, nitrogen, oxygen, argon, are transparent to infrared radiation. They don't interact. The photon doesn't see them. It can only interact, a long wave photon can only interact with greenhouse molecules. Now, it turns out they're all about the same. There isn't any big difference between methane, CO2, water vapor. Trust me, they're all about the same. But I'm going to use carbon dioxide just for fun because that's our demon gas. This molecule absorbs the photon and then vibrates with more energy. And there's a video in the community on how that energy vibration works. It's called the dipole moment. And I'm not breaking that down here. And it's possible a few different things can happen then. This vibrating CO2 molecule could hit an air molecule or an oxygen or nitrogen and transfer its energy mechanically to that air molecule. And this is conduction. And so the air heats up. And that's why we have a, hot summer day. Coming down, the high energy photons do not interact with oxygen and nitrogen. So the only way to heat the air is on the way back up, hitting a greenhouse molecule. Thank goodness we have them. And then transferring its energy mechanically to an oxygen or a nitrogen molecule, right? Or it's possible that the CO2 molecule will take that higher energy state and immediately re-radiate one or two new long wave photons out in some random direction and then go back to the way it was before. It was bouncing around before. It bounces around crazier for a bit of time, and then it re-radiates one or two photons out. And that bit of time is like a billionth of a second. It just happens immediately. So that the photon's annihilated and one or two, typically one, gets re-radiated out. But the photon isn't bouncing off. It's getting absorbed and re-radiated. And that's what we're going to look at now. Because this is the greenhouse effect. The photon goes on a random walk, and we read a bit about it in the homework, and I discussed it with the sun taking 150,000 years. And so it takes this random path in random directions. It doesn't have to be trying to get out. It's just going in, it's just bouncing around like a pinball in a pinball machine, okay? And if any photon ends up in the 10 to 14 micron range and it's pointed enough up, it'll escape to space because it goes out through the window. Otherwise, it'll keep hitting molecules, getting absorbed, new photons re-radiating up, down, all over, sideways. And it's not one photon bouncing, it's photons getting absorbed and re-radiated, but it happens billions of times a second. And with more CO2, the residence time near the surface increases. The residence time is what's key to this, and we're going to go into this. Eventually, I'm just talking about the emission height right now. Eventually, after billions of random collisions, and this is what the homework was about, the long wave photon goes up high enough to get out, just like the ones on the sun. The emission height is a calculated average height where many photons escape, as many photons can escape as don't escape. It's just a calculation. You can't measure it. You can't see it. You can't say what it is exactly. It's just a calculation. It's not the same as the tropopause, but it's pretty close to the tropopause. And it depends on different factors than the tropopause does, because if you added more CO2, then that would change the emission height, where that would not change the tropopause. All right. But they're pretty similar. On average, you can think of the emission height as about 10 kilometers up, but sometimes it could be 8 kilometers, could be 12 kilometers, could be 5, okay? That's the emission height. Now, at that point, the photon finally just radiates away into space. It's not interrupted anymore. So it just goes off into the solar system, just like the one on the sun did. And this photon has traveled on average about 3,000 kilometers at the speed of light. It takes about 10 milliseconds to go the 3,000 kilometer journey. It will finally go to space. It's not heat. It's a low energy photon that you can't see. So if you looked at Earth from space and you saw a blue ball with white clouds, none of that. Those are all high energy photons reflecting. This is just a long range, a long wave photon just going off out into space. And there are gazillions of them going all the time out to space forever, till they hit some other random thing light years away or whatever it is, okay? There's another final concept here, and that's the emission temperature. The emission temperature is just the temperature at the emission height. That's all it is. There's no steady emission temperature, but it's going to be around negative 50 degrees centigrade plus or minus. All the energy that goes up from the ground eventually escapes to space via long wave photons, all of it. These are pretty cold photons, but they all add up to the amount of energy that hit the surface originally to warm it up. So this is two concepts, the emission temperature and the emission height, and they're both calculated, not measured. One person asked yesterday, in the homework where I've got these zones like 1 millimeter and then 1 centimeter and 1 meter. Is that reality? No, it's not. That's just breaking it down just for expository purposes, just to give you an example. But in reality, it's just a gradient. Now we're ready for the greenhouse effect. All right, so here we go. With those concepts in place, what is the greenhouse effect? Now, you maybe heard that the greenhouse effect is the difference between the temperature we have now and the temperature without any greenhouse gases. Have you heard that? You haven't? Well, that's very common and it's wrong. It's a terrible concept because with no greenhouse gases, there's no oceans. There's no storms, no clouds, no plants, no animals, and no us to figure anything out. The atmosphere would just be nitrogen and oxygen, and it would have its own characteristics of heat transport. And so it'd be so different that it doesn't make any sense to think about it that way. So Javier says, the greenhouse effect is the difference between the ground temperature and the temperature at the emission height or the emission temperature. And that is really the responsibility of the greenhouse gases, because remember, the atmosphere is transparent to these long wave photons. They don't interact. The long wave photons do not see the atmosphere. They only see or interact with water vapor, CO2, methane, and argon, methane and ozone. That's all they interact with. They can't hit anything else. So sometimes this greenhouse effect is pretty big, and other times the greenhouse effect is pretty small. It depends on a bunch of things. In fact, we're going to see that sometimes the greenhouse effect is negative, which the IPCC does not tell you. So here's kind of the best way to think of it. Greenhouse gas molecules slow the escape of photons, but they don't trap them, keep them, or destroy them. This is exactly what a sweater or a parka does. So imagine you're just in a t-shirt out in the cold and you're shivering and losing a lot of millions of infrared photons every second. You're freezing. So then when you first put on a sweater, the sweater's also cold. So for a moment, you stop giving off heat as those long wave photons get stopped by the sweater, interrupted. And then after the sweater warms up, what does it do? It increases the residence time and makes the escape path longer for those photons. And those photons then have a chance to warm up some greenhouse gas molecules inside, and then those will transfer, or they will hit sweater molecules, and they will transfer energy to those molecules mechanically, and you'll have more re-radiating infrared coming back at you, and that's insolation. So it's your body energy. It's just been paused for a minute to build up. And now when it's at equilibrium, you're now radiating out the same amount as you did before, but you're trapping is kind of the wrong word. You're retaining some of those photons near your skin to heat up the air near your skin, and that keeps you warm. Okay, and that is essentially the greenhouse effect. The sweater plays the role. The sweater can intercept those long wave photons, and it plays the role of CO2 in the atmosphere, but it's pretty similar. It's a good concept because it can't trap the heat forever. And once it gets back to equilibrium, all the energy coming off of you eventually leaves the system. Now I want to go back to the lapse rate to understand how this affects the atmosphere. Now, suppose the atmosphere is stable at, let's say, 300 parts per million of CO2. And the emission height is, in this case, let's say it's 8 kilometers. All right, now we add another 100 parts per million of CO2 to the atmosphere, as we actually have in the last 150 years or something. What does that do? Initially, it delays many photons, causing them to take a longer path upward, but pretty soon it reaches equilibrium. Now the path is longer and more complicated, and it takes more time for all those photons to go up. And because the atmosphere gets warmer, and because there's that longer path, the emission height rises. Magic. With 100 more parts per million, the emission height will go up. As the emission height goes up, the emission temperature doesn't change. That's the temperature of escaping to space, just like before. So the temperature rises. So if you think about it, the whole gradient moves up. The temperature at the emission height doesn't, but the emission height itself does. And so that's a little bit like adding a second sweater on top of the first one. And it's a pretty good analogy because the first sweater does most of the work, most of the warming, and adding a light sweater on top does not do much less, but it does a little bit. And the temperature goes up, but not by much. So we say, I'm going to do this again. We say that we slide the lapse rate to the right. Watch what happens. Now we have the same temperature at the emission height, but we have a longer path. And yes, it gets warmer by some tiny amount. Nobody knows how much. Some people will say 1 degree. Some people will say 5 degrees. Some people will say it's negative. But theoretically, it has to raise the temperature here because we have a positive lapse rate. Because as you raise the emission height, you get more energy bouncing around near the Earth, and you get more of the sweater effect. And so the temperature has to go up. It's like adding a second sweater. In the last 100 years or so, what's happened is the emission height has actually gone up by about 150 meters because of humans adding CO2 to the atmosphere. We didn't probably add all 100 parts per million, but we maybe added 50 to 80 of that, 50 to 80%, and then some of it came out naturally. Maybe. Nobody knows. No one can measure any of this stuff because the real world is not a laboratory, and there are tons of feedbacks and adjustments, and it's different in different latitudes. And the heat pump we're going to learn about treats it all differently. So this extra bit from 150 meters rise in the emission height may or may not be measurable in the ground. And this is why we are spending trillions of dollars to decarbonize our economy. Right here. Here's the chart again. Red side, over here is high energy. Over here is low, very low energy. And this is kind of the number of photons going out. So just look at the dark blue line. Number of photons going out. And we'll just break all this down. So we're going to start with, just on the right side, we're just going to look at long wave radiation going out. And the first thing we see, where is it, is the atmospheric window. This is the atmospheric window. You can see that nothing gets in the way. This is the total absorption and re-release of, the delay. This is the total greenhouse effect here. And over here, there's nothing. And we'll get to this little part later. But that's where photons in this range can get out. And now we're going to break it down by its constituent molecules. So here's water vapor. Water vapor does a huge amount of, let's say, blocking and re-radiating the outgoing flow. It's a sweater. There are 2 sections of blocking, 4 to about 8 microns. In this area, it's blocked. It doesn't matter what other molecules are here. It's 100% blocked already by water vapor. And there's a lot of photons here, so it does a huge amount of work. And then in the other section over here, water vapor starting at about 12 or 13 microns gradually goes up so that by the time you're at about 17, 18 microns, water vapor blocks everything here. And this is, again, full on saturation of the greenhouse effect, but there aren't as many molecules here in this area. But it certainly blocks all of them and makes sure that they are delayed going out to space. And now we'll look, and so after about 30 microns, which is over in here somewhere, it just doesn't matter. It's blocking, yes, but there aren't very many. Okay, make sense? So now here's carbon dioxide. Carbon dioxide only blocks in the 14 to 16 micron band, around 15. Okay, but water vapor also covers a lot of that. So that makes CO2 less effective because water vapor is always doing it. So if you raise or lower CO2, there's less of an effect. Water vapor hasn't changed. They're both doing the same job. So there isn't much chance to overcome that. There's a little, and it's important, and we're glad it's there, but much of it in that range is water vapor. Okay. If you look at the two combining in gray, you'll see we're already there. Right now, no amount of CO2 can do more because it's already done. We're mostly blocking here. It's 90% or more greenhouse effect already. All right. It's essentially, we call it saturated. Now I want to look at oxygen and ozone because it's interesting because here there's a little spike in the window caused by oxygen. Ozone is just 3 oxygen molecules, oxygen atoms. But all of this, it happens in the stratosphere above the tropopause, where it's not going to come back and warm the Earth. It warms the stratosphere. Yes, it's actually very strong in the stratosphere, and it makes the stronger. It's so strong that it reverses the lapse rate and causes the stratosphere to get warmer as you go up. Oh, now it's time for methane. Methane is also practically covered by water vapor. Not 100%, but methane or no methane, the water vapor is doing much of the work. More methane isn't going to do much at all, as we're about to see. So first of all, how do we know this is right? I want to explain this paper by Will Happer and William Van Wijngaarden, who have done probably the foremost atmospheric physicists in the world. And they calculated what the values would be for every wavelength. This is called a wave number, and there are thousands of them going across the spectrum, would be how that would turn into the shape of the greenhouse effect for the Sahara, for the Mediterranean, and for Antarctica. And the first thing to understand is the Sahara and the Mediterranean are both deserts. And so they're very similar. But they calculated these in science. This is a prediction. This is like, okay, if the equations are right, we should see this. And then they compared it against the actual observed results, which we get from weather balloons. Weather balloons measure, for every wavelength, they can measure these effects and see that this curve is almost identical to the one they calculated, and it's within 1%. So these guys are very, very good at what they do. They understand how these interactions with all these molecules work, and they made predictions that are accurate. And as Feynman said, if your prediction doesn't agree with the data, then your prediction is wrong. Your theory is wrong. Go get another theory. This prediction is right. And so their theory is right. So what they say is right. And anybody on social media who says that Will Happer is an idiot is an idiot. The interesting thing here is that this is CO2 at 15 microns right here. And this is the greenhouse effect from CO2. And then in Antarctica, I don't know if you've heard this, the greenhouse effect works in reverse. And CO2 at both poles causes temperatures to go down. It makes it colder. More CO2 makes it colder at the poles, not warmer. And this is only for the 9 months of the poles when they're in the dark. And when the summer at, let's say, the North Pole, you get direct sunlight coming in, then you have a fairly normal environment, and the greenhouse effect works according to the normal lapse rate. But when it's dark above the Arctic Circle, the lapse rate is negative there because there's kind of a permanent, for 9 months of the year, there's a permanent inversion where you have higher temperatures above and the ground is colder. Remember, the poles are essentially deserts. There's hardly any water vapor at the poles. And so CO2 does a tremendous amount of work at the poles to cool the surface. Okay. You may not have heard that from the IPCC. We all exist because there's a greenhouse effect. If there were no greenhouse effect, the Earth would be way too cold for life. But water vapor does most of the work to insulate the planet. And if there were no CO2, the Earth would be maybe, it's hard to say, maybe 5 degrees colder, but only bacteria would live here because we all need CO2. The plants all do, we all do. And as we're about to see, we don't need much. So now we're going to the fourth section, and that's the diminishing returns. This is again Will Happer and Van Wijngaarden showing scenarios. So far, so good? All right, this is the fourth module here. So this is a visual representation of the equations. This is all the right side of the graph that we saw before because this is all outgoing long wave. But now we see scenarios. So the x-axis again shows the short wavelength on the left, long wavelength on the right. You sort of look from the bottom up. This is kind of, think of it, this is blocking. Here, there's no blocking here because this is the atmospheric window. Here, there's a lot of blocking. Here, there's a certain amount of blocking, okay? The gray curve here represents 0 CO2. So if there were no CO2 at all, we'd still have a greenhouse effect. That's this area up here. And that would be from water. This is the water contribution. More in the higher wavelengths and less in the longer wavelengths. And we saw that in the previous graph, okay? Then this fuchsia pink curve here represents 50 parts per million of CO2. And this is what you get. It's dramatic. It's huge. So now we'll go and add, we'll start doubling. So now we're going to add 100 parts per million, and we get the green curve here, which also does some blocking. These are called the wings on the side. Okay, the central part is just taken out. The 15 micron band is taken out by 50 parts per million. That's done. Now we're talking about the 14 and 16 micron bands over here. It's that difference between the green and the pink. See that little triangle in there? That's the difference between 50 and 100. And again, the green and the pink is over here for the 16 micron. So then if we go to 200, we double again. That's the blue. That's this blue here. And again, we have this little white area here, and we have this white area here. And, you know, maybe that represents 1 degree or not. It's hard to say because you can calculate it, but we don't know what the actual temperature would be because there'd be a lot of adjustments, right? And then this is from 200 to 400. So the Earth has been at 200. Recall from our first day's lesson, the Earth has always been at 100, 200. It's never been below that, 200 ppm. It was born with hundreds of ppm. It's in the rocks. It's in the atmosphere. It was here when the Earth was just a molten ball of lava. It's always been here. And so we've never been below this blue line. And once or twice we've been down in the high 200s, and not that long ago. And plants hate that. It's much harder for plants. Everybody should understand, we are in a CO2 starvation regime right now. We're at the very lowest possible CO2 for life. If it went down, plants would go away, and so would all the animals. But going from 2 to 400, that's this area here. That's this white pixels in here. And here we have 2 to 400 on the left wing. Maybe that adds a degree, but maybe it doesn't. And then finally, from 400, which is where we are today, to 800, which would cause most of the staff at the New York Times to jump out of their office windows to their deaths. We don't get a lot more warming. This is 800 parts per million right here in red. And I don't know, it's maybe a little warmer, maybe a little less warm in here. That's, at the 50, it's a little less. Here, it's a little more. It might be 1 degree. So from 50 to 800 parts per million, sure, there's some warming, but we've never been at 50. We've never been below 220, I don't think, as far as I know. And so the warming from there, sure, yes, of course, there is some warming. How much? Nobody knows. Probably not bloody much. So I'm going to use an analogy to express this of a football goal. Imagine there's no goalkeeper for this team. This team just doesn't have a goalkeeper, and they're professionals, but they don't have a goalkeeper. So in one whole season, representing 0 parts per million, in one whole season, the opposing teams may score 200 goals in a season because it's hard to play without a goalkeeper. And this is the same as no CO2. But let's say there's 25 parts per million. Well, that's the equivalent of 1 goalkeeper in this made-up scenario. And so 1 goalkeeper can stop a lot more than 0. So he stops 20. So 20 goals go through in a season, which might be average. I don't know football statistics, but let's say. And then when we double to 50, we add another goalkeeper. And now, it's more than half. It's less than half go through because they're pretty good working together and they can now block 6 goals in a whole season of, I don't know what a season is, 50 games, 60 games, I'm not sure. Then from 50 to 100 parts per million, we double again. And sure enough, 4 people, it's a big goal. And the extra 2 people help a bit, not much, but they prevent all but 2 goals are scored. And then we double again to 200. Now you got 8 guys standing in the goal. That's going to be hard to score against. With 8 guys standing in the goal, maybe the opposing team scores once every 4 or 5 years, maybe, but most years it's 0. And that's essentially where we are with the effectiveness of CO2 now. It's a logarithmic curve. The first 100 parts per million do much of the work. This is the area under the curve that represents the blue shading that represents the greenhouse effect. But by now, up into 400, we're just really at diminishing returns. From 400 to 450, 500, this is just crazy territory as far as the UN concerned. That would be the end of the world is here somewhere. But the added greenhouse effect is just not much. And if you doubled it to 800, again, you're just not getting much out of it anymore. If you doubled it again, to 1600 or 3200, you just aren't going to change the conditions on Earth very much. Let's look at methane. All right, methane, terrible, most potent greenhouse gas of all, evil. And right now, what's methane is about 2,000 parts per billion. 2,000 parts per billion. Why would they use 2,000 parts? Why would they use parts per billion? Well, because 2,000 is a bigger number than 2. 2 parts per million is the same thing, more or less, but it doesn't sell as much fear. 2,000. That's just a scarier number. So it's marketing. Methane blocks infrared radiation at 8 microns. And if you recall, it overlaps water vapor a lot. So it's mostly covered. I mean, you have to look hard here, but they've calculated it. And if you just look in this white, 3 or 4 white pixels here between the red and the black, that is a doubling of methane to 4,000 parts per billion, which is really 4 parts per million. And realistically, we could vent all of the natural gas we're drilling now and not burn it and get to 4,000 parts per billion, maybe in 50, 80 years. It just takes it's just a ton. It's just a ridiculous amount of methane. We can't get anywhere close to it. All the cows in the world couldn't really change the amount of methane much, and they have no effect on climate because methane breaks down in bright sunlight and eventually turns into CO2, water vapor, and a bit of formaldehyde. So not only is methane an impotent greenhouse gas, it also doesn't last very long in the atmosphere. So the parts per billion don't matter, because if you add more parts per billion, you're also removing them. No number of parts per billion has any impact because methane doesn't contribute to climate, and it never has. So the more you know, the worse this gets, because journalists don't do any homework. More CO2 is actually better. While adding CO2 has a tiny warming effect, which I would say is good at this point, because in a couple thousand years, things are going to get a lot colder. It has a huge effect for plants. And if you look at these red dots, that's where NASA has found that the Earth has gotten greener in the last 30 years because of the CO2, the extra CO2. And plants prefer it. From a human perspective, the Earth has never been greener than it is today. It was 50 million years ago, but it hasn't from a human perspective. CO2 is not pollution. More would be better. How much? It doesn't matter. The Earth has had 7, 8, 9,000 parts per million plenty of times in the past. Life was great. And it just doesn't play a role in quality of life.
So, yeah, just a comment on that. In the HAPA paper, it says, oh crikey, I got my window is all mixed up. But the comparisons of the curves that they calculated and the measurements were from a Michelson interferometer from a satellite,
and from radio, and from the
It doesn't mention a balloon there. It doesn't mention a balloon there.
That's interesting. So, like I say, yes, theoretically, you double CO2, you get a degree of warming, and the IPCC says you get 2 degrees of warming, or whoever wants to calculate it. But in reality, not so much. From here, we're going to move on more toward the heat pump and how the weather system actually moves heat. And we're getting away from this radiative balance nonsense where all the energy coming in to the earth has to go back out. Well, yes, but not at the same latitude. And that's where NASA and the IPCC failure by omission doesn't tell you that a lot of the energy goes into the oceans, runs around in the ocean system, and then eventually makes its way to space over the poles. They don't talk about that. So these radiative balance diagrams where you have as much coming in as going out, that's just nonsense. It's not true at all. You do over the earth as a whole, but not at anywhere on earth is that true. There's always a deficit or a surplus. And the surplus goes into the weather system and makes our weather and makes our climate, and then comes out at the poles, which has a huge surplus. Much more energy leaves the poles as goes in, much more. And much more energy comes into the tropics than leaves the tropics. So it's not an atmospheric effect, and no amount of atmospherics is going to get you, to balance any equations, because they don't balance. And that's a big part of the ruse right there. Said, look, we can show you that more CO2 causes all this warming because it has to be in balance. No, it does not have to be in balance, and it's never in balance. The radiative effect is different from the thermal effect, and the thermal effect is what runs the climate. The radiative effect does not run the climate.
Question about, you mentioned the CO2 effect at the poles is actually negative or inverse?
More CO2 makes a colder surface temperature.
Yes. Does that affect the ability of energy escape to space?
No. It's a very good question. It's an excellent question. And the reason is that most of the energy, and this is actually fascinating, I'll just take a second. Most of the energy arriving at the poles arrives through the atmosphere above the inversion layer and then moves up. So let's say, think of it as it comes in at around 2,000 to 5,000 feet of weather. And then once it's inside the vortex, it has nowhere to go but up. And NASA can see this. There's satellites that can see this going up. Now, is it very cold? It's very cold. Is it a tremendous amount of heat? It's a tremendous amount of heat. Okay, it's all freezing cold, but it's a huge amount of heat going straight up, out through the vortex, or over the pole, and it's in the winter time for each pole. So when we'll talk about that more as we talk about the heat pump, so I won't get into it now. But that negative relapse rate is essentially a kind of a not part of the equation. It's not part of the system. It's just the result of an inversion. Because so much warmer air is coming from over Canada and Siberia, it's moving poleward, it traps that cold air underneath it and gives you an inversion. And that's during the dark months. And then in the summertime, that changes back to a more normal situation. And then you have much less energy escaping to space during those 3 months of summer.
Okay.
Complicated, isn't it? It's not what
it is.
Time magazine isn't going to tell you any of this because doesn't sell them any advertising.